Okay, so this is a week 10 of Psych 3280, Neural Basis of Consciousness. And today I'm going to talk about integrated information theory of consciousness. So to recap the contents of the week 9, I first demonstrated that attention can operate without conscious experience of an object. And as an example, I started off with a blindsight situation where blindsight subjects were cued by invisible stimulus, and then blind subjects' performance, namely reaction time, improved on the cued location, but slowed down on the uncued location. And still, blindsight patient said that neither cued or target stimulus was invisible for him, and performance, detection performance-wise or localization performance-wise, he was above chance, but not really different for with and without attention, the cueing stimulus. And then in the second example, I showed that the sort of similar homologous experiment in healthy individuals using continuous flash suppression to suppress the searched for target, yet their eye movements tend to move towards the location of the hidden invisible target that they're attending to and searching for. And then finally, I showed also the Bahadur-Barami's experiment where using fMRI, they again used the CFS, continuous flash suppression, to suppress the intact object. And then the location of the V1 that corresponds to the stimulated location increased its activity when subjects were not paying attention to the demanding task at the center, whereas when they are doing some simple non-demanding task at the center, the activity in the V1 spread to this invisible object much stronger. That's an evidence of the neural amplification with residual attention left from the central task. Okay. And then the second part of the video, I discussed evidence for consciousness without attention. And here I mainly talked about the details of the dual task paradigm, and especially my student, a previous student, Julia Matthews' paradigm, where we looked at whether we can perceive faces or red-green disks without top-down attentional amplification. And attention was there controlled by the highly demanding central task always. And under the same attentional conditions, in the case of the face genders, people were able to see the gender of the face without training and with metacognitive accuracy. So that uncovers or that sort of resolve the previous problem of the dual task paradigm, which is associated with the lengthy training and the possibility of unconscious response in the dual task paradigm. On the other hand, the red disk circle, red-green disks were not possible to discriminate without attentional amplification. And that was true even we rescued the task with the partial report paradigm. So there was no confound or demand of the memory, but still they couldn't see it. And the final killer experiment that we reported was that attention, that object where faces were painted with the red and the green, and then subjects reported that under the no attentional amplification situation, they were able to see the face aspect, but not the color aspect of the disks. So that is also backed up by the psychophysics performance with the metacognition only for face, but not for the disks. And the important thing I emphasized was that the difficulty of the task for the face and disks were always equal when they are done as a single task performance. And these differences only emerged under the dual task paradigm. And then towards the end, I discussed that, so before that, the important thing was for you guys to understand that the logic of the experiment. not too much for the conclusion of the experiments, and also how asking how conscious perception is manipulated and measured, as well as how attention is manipulated and measured in these paradigms. And then towards the end, I discuss about the sort of the attention equal activation amount equal the degree of consciousness, and also amount of attention type. Simple idea of sort of the scalar amplification of things always gets to consciousness or attention kind of idea, which is very naive, but still predominant across all the domains of research, from philosophy to neuroscience to psychology. But these are pure, basically, impossible to, reconcile with all this knowledge that I tried to deliver to you over the last 2 weeks. One is that attention operates not only for amplification, but also suppression of the unwanted stimulus. That's one thing. And also conscious or unconscious is not a matter of the degree of the activation. And that's one of the things that I'm going to talk today. So that's one thing. And then as an alternative to explain consciousness as well as attention is that it's not the amount of the activation itself, but the patterns of activation or complexity or informativeness or relationship between the of the activation between the neurons. That's the sort of the entire bigger picture of the lectures going from week 10 to 12. So then in week 10, this week, we will introduce the integrated information theory of consciousness. And this is basically focusing more on the relationship complexity and also information aspects of the process, but more important aspects I'm going to explain. And this week I will discuss this without any mathematics. And next week I'll introduce a little bit of mathematics, but don't worry, I'm not gonna use lots of equations. Okay, so the learning objective of this week is to be able to answer the following questions. First of all, what is IIT? It's difficult question to really correctly and fully answer, but the overall general answer to this would be enough. Integrated information theory and how it goes from where and then and where. So basically, where does IIT start, which is phenomenology, and then to construct a theory. Okay. And then what are the 5 core properties of everyday phenomenology that IIT considers important? And that's also, explicitly stated in the slides, so it should be easy to find the answer. And what is a neural measure that was inspired by the IIT? And that's also the last part of the video, so it's also easy question to address. And as a reading material, I put one of my paper written for the philosophers, so written in a journal called the Philosophy Compass. And this one also doesn't use much of the equations or mathematics and intuitively explain IIT. So if you're interested in this topic, please take a look, but you don't have to read this paper to answer the quiz for this week. And then in related to this type of the thing, starting from last week, I said that we are coming closer to what we are doing in the lab. And this week's topic is also related to what we are doing. So I'll take this opportunity to advertise a little bit of the potential honors project at our lab, Monash Neuroscience and Consciousness. So for example, this link will give you this candidate categories of project available for our lab this year. Mainly characterizing structure of conscious experience. This is a psychophysics experiment using similarity rating or massive report paradigm. And the second one, testing the isomorphism between the structure of information and the structure of consciousness. This is a part that we are interested using IIT. And then the third one, mathematical modeling of phenomenological structure. This is more mathematics kind of project. So I will only explain to the to people who are interested in this kind of things later. The other thing is that this YouTube link, it's an going into the details of the how IIT computes each of these quantity that I briefly covered in this lecture. And if you're interested in that, then reading the papers that are mentioned in this this tutorial or watching this 2-hour video may be a good starting point to get used to the IIT. All right, so the first part of the lecture addresses and also recaps the very first lecture that I gave for this course. Why do we need a theory of consciousness? So week 1 to 7, I tried to establish a basic building knowledge for the consciousness research, starting from neurons and also especially the visual cortex, early visual areas in anatomy and physiology. And then there mainly I discuss about between a relationship between consciousness and the brain, but in a loose sense. Okay, and then week 8 and 9, we came closer to the latest research on consciousness, especially through the lens of the relationship between consciousness and attention. It's still like controversial kind of topic. And then, as you might have already felt, the knowledge from week 1 to 9 is already quite large. And how can we make sense of all of what you learned? And if you have been attending to all these, tutorials or amount of the research that has gone on from 1990s, it's really huge. So one reason why we want to have a theory of consciousness is to understand all these findings in a coherent manner and to make a useful prediction. And then another thing is that we want to address the core question of consciousness by extending these approaches. But empirical question always generates further question, but it doesn't necessarily get to the core or original kind of question, such as why the vision feels very differently from audition, or why do we ever feel anything after we wake up, and so on. This is so fundamental, and sometimes this kind of fundamental question has to be addressed from a more theoretical or basic point of view. And then important thing is that also to make a further progress, we need a theory to make not only explanation for the findings in the past, but also to make a prediction for the future. And that's another role the theory of consciousness has to play. So this is the slide that I gave you as a sort of brief history of consciousness research, starting from philosophical discussions and Descartes, and then some psychology fathers, Fechner and William James, and then 1990s and so on, neuroimaging studies has started to explode, and then David Chalmers pointed out how the problem of consciousness, and then now today I'm going to talk about this in Tononi's integrated information theory of consciousness. So around 1990s, not only the explosion of the neuroimaging studies, but also Christoph Koch and Francis Crick started to propose a research program to find the neural correlates of consciousness, the NCC. And here, what they propose essentially is that you have things outside the world, like in seeing the dogs and people, and then when you see it, something happens in the eyes, and then that gets delivered to the visual cortex, and then to reach to somewhere in the brain, and then to activate the neurons, and that neurons activity is always corresponding to subjective conscious awareness of this, dog. And I showed this figure in the first lecture, and at that time I didn't mention this explicitly in the lecture, but here as you can see from this figure, Christoph Koch, my supervisor at that time, was probably thinking more or less like, hippocampus or amygdala or somewhere where he was recording a single neuron from. If you remember a couple of weeks ago, Jennifer Aniston neurons and also Sydney Opera House neurons were discovered around here from epilepsy patients. And also IT cortex that has an object selectivity that's located here. And these high-level visual areas attains, have an population of neurons whose firing tend to correspond to some kind of concept invariant to the detail of the figures. And that was sort of proposed sort of a subset of the neurons that are tightly and strongly correlated with any particular one percept. That picture was already kind of indicative that it's more or less a neural correlates of a consciousness, but also more to do with a high-level conceptual structure or something that is reportable to from the subject. But it's less to do with this qualitative aspect of seeing the dog, like fluffy furs or shape of the ears, or the color of the blackness of the nose of the dog. This type of stuff is likely to be located more to the with the posterior part of the brain around here. And also what for some reason we still don't understand, but the pattern of the activity of the neurons across the brain is in some way coherently generate some quality of experience, like seeing dog in this way, but not the other. So the NCC program itself is implicitly assuming that there was something to do with the population of the neuron activity. And then our path so far, especially from lecture 1 to 7, was to guide you, and also, this is actually the path that many of the researchers since 1990s or even before have been taking, like trying to address the empirical question: is V1 located within the NCC, or is attention and consciousness different, or is the frontal lobe related to consciousness? And then eventually mapping the NCC across the brain to arrive at the sort of the question, the answer of holy grail of neural basis of consciousness. That's sort of the strategy. And this type of a strategy has been criticized by philosophers. Sometimes they call it this type of approach as a easy program or extension of the previous studies. So their category is that categorization of this type of approach is that this type of the study is just trying to explain observable behaviors from the neural activities, and it doesn't get to the sort of the top of this mountain, which is the hard problem. And here the approach can be summarized as any kind of the research program trying to find the correlational evidence between the conscious perception and its report with neural activity. It doesn't matter whether you use the perturbation like TMS to stimulate the brain to break the correlation into the causality, but it's as long as you have trying to establish conscious perception on one hand and the neural activity on the other hand, then that's a sort of correlational laws as best as you can. And that kind of approach is not going to get to the top. That's what they are saying. So it is the same kind of criticism or question that I repeatedly came back during the course of the lecture, where for example, when I talked about face areas or color areas V8 or visual motion area MT, somehow it seems like the activation, artificial activation, stimulation of the MT neurons seems to generate a seeing of the motion, or stimulation of the FFA generate a face perception and so on. So activity of the neurons in particular area in the brain seems to generate some qualia, particular aspect of the consciousness in us. However, why these type of the neurons activation result in this qualia, this part of the arrow is very difficult to understand. And if there isn't any kind of function or any kind of rule that says such and such neuron's activity and the connectivity has to result in this conscious experience, then we are in a much better situation, but we are far from that kind of laws. And in fact, I also mentioned that if you look at each of the neurons, say FFA or MT or B4 or BA, probably at the level of the individual neurons, there is nothing that we can find that is specifically related to each of the qualities, such as motion, or face, or color. There's no molecules or synapses or action potential that corresponds to the quality of the seeing of the face or motion or color. And what it is that generates this in particular qualia, that's a question, and it's a hard problem. So according to some philosophers, these kind of hard problem can be logically argued that it is in fact hard. And some of the arguments are listed here, such as zombie argument or inverted qualia argument or knowledge argument. And basically, what these are saying is that why or how certain neural activity must give rise to consciousness cannot be explained in this order, in this type of approach, because we can logically, or we can at least imagine a world that is consistent with the non-physical laws in the physics, such as electromagnetism or gravity, and also particle and so on, which has everything consistent with what we have, but some people who exist in this world who doesn't experience color, even though their B4 neurons or B8 neurons are wired in the same way as us, and then activity also give rise to something very similar to us. Every aspect of the brain and molecules and chemicals are all the same, but as long as we can imagine this entity, philosophical zombie, which doesn't have any qualia, or those people who have completely inverted qualia, like when I experience blueness on the screen, that particular person may be inside experiencing yellow. And then if all of the history and also all the language usage or meaning is completely inverted across the red, blue and yellow between me and that person, then we may not be able to detect any kind of the difference behavior. That's a sort of inverted argument. And knowledge argument is that we can imagine a neuroscientist who was born without seeing any color, and then raised without seeing any color, and then but still that particular person, Murray, famously, learned all the neuroscientific knowledge up until the university or something like that, and then she absorbed all the knowledge about the color experience and the color psychophysics and the color neurophysiology, but she has never experienced the color by herself. And then when she was first exposed to the color outside the world, in this hypothetical situation is that Mary was raised in a black and white room for all the way up to here, and then if she can experience this color for the first time, does she gain anything new other than what she has already learned? And as long as there is something above and beyond, then what is it? That's a sort of the question they're addressing. In my mind, and also, those of you who have followed the lectures so far, all of these things are not really empirically, possible, most likely. For example, the knowledge argument is, I think it's completely flawed that, if the person who can experience the color for the first time they see in the world when they are exposed must have, most likely, the color experiencing circuit in the brain. So they should probably also experience the color through imagination or dreaming. But anyway, so I'll cut the details of the argument. But Anyway, the important thing is that there is some kind of argument, philosophical argument to say that there is a gap between these standard neuroscientific approach to the hard problem of consciousness from bottom-up approach. And these are, in our empirical, terms, it can be condensed into the phrase like, why do we perceive phase color motion when our neurons in FFAP8 MT are stimulated in particular way? And that seems arbitrary. The link between the neural activity to the particular conscious experience seems arbitrary and can be swapped or can be removed or can be sort of added. That's the reason why philosophers argue that there is a huge gap between the empirical research program to the hard program. So now the rescue comes from the IIT. So IIT is not the kind of approach so far, in the sense that it tries to approach hard problem from the top, like this helicopter in this figure. Okay, not IIT doesn't actually deny or or inconsistent with this kind of bottom-up approach to get to the hard problem, but also it tries to give a theoretical guidance from the top to arrive at the hard problem. That's a metaphor. And basically what it tries to do is to try to come up with the explanation on how our conscious phenomenology can be supported by physical mechanism. It's not the other way around. How our physical mechanism produce conscious phenomenology, that's a hard problem. However, how our conscious experience is supported by at least this kind of mechanism that satisfies this condition, then it may be more amenable to explain consciousness or approach to the hard problem. And eventually, this kind of approach may vanish the concept of the hard problem, possibly. So, in other words, integrated information theory reverses this arrow. If we experience dog in this way, but not other way, then that kind of experience must have been supported by such and such condition in the physical world. That's the logic of the IIT. So how can we start building a theory of consciousness? The proposal that IIT makes is that first we should start with identifying the key properties of consciousness. And that is what they call as a phenomenological axioms. And that includes information or integration, exclusion, existence, and also composition. I'll go into that later. And then propose the properties that physical system must have in order to support these identified properties. So these are the logic of IIT. And in the next video, I'm going to explain how it does it in a little bit more detail. Okay, so now I'm going to introduce integrated information theory of consciousness. So this is a title of the paper by Oizumi, Albantakis, Tononi in 2014, and it is actually capturing the most important aspects of this theory. It says from the phenomenology to the mechanism of consciousness, integrated information theory 3.0. The first part, this phenomenology to mechanism. This is the essence of what IIT is actually, from here to. It's not the other way around. That's the important part. Okay. So from the phenomenology part, what IIT tries to do is first to identify 5 essential characteristics of any conscious experience. And this is called axioms in IIT literature. And what it means is it's supposed to be any kind of the true nature of the consciousness when you think about it carefully. In any of the example of the conscious experience. And it may not be immediately understandable or easy to understand, but this is a kind of
most important aspect of the theory. And most likely, you may have some questions, but then I'm happy to answer the questions over the forum or emails if you send me. Okay. The first one is intrinsic existence. So this, what it means is that the consciousness always exists for the subject who experiences that. And it is an existence for the systems itself. Okay. And then the second aspect is composition. Any experience, any moment of experience is always composed of various aspects of the things. Here, by the way, this is an exemplar sort of, drawing based on Ernst Mach, philosopher in the 19th century, a physicist as well. And this is a sort of drawing of his own body, on the chair, looking out to the window, and on the left side there is a bookshelf. And this part is the sort of his observation of his nose and beard or mouth from your left eye. And as you can see on this side, there is a blue book and on the left side, and then there is something blue in your clothes. And these are the kind of the parts that compose your experience. Okay. So another aspect is the information. Information in IIT is a bit different from information in other sense, as I come back to later on. And what it means is that it is an informativeness or differentiation of many more different possible experiences that you could have. And any moment of experience is informative as it is, because of the way it is. So if you are experiencing the moment like this way, then the way the experience feels or experience is very different from any other different moment of experience. And in that sense, it is informative. And sometimes we also talk about it is a reduction of uncertainty among all possible experience to one particular. And that can be one way to consider this information action. Then integration. So integration action of the IIT means that any moment of experience is always integrated and experienced as a whole. For example, in this case, it is this figure shows that experience is never like experienced independently on the left half of the visual field and the right half of the visual field. It is always experienced as one thing at a time. It's not like each of the parts are experienced independently and cannot be accessed or experienced in separately. This seems a bit contradictory to composition, but it is integrated always and then composed, and that gives you uniqueness or informativeness of the experience at one time. So after the existence, it's kind of related to each, and then composes or sort of specifies essential characteristic of consciousness as a whole. And then the final one, final actions of the phenomenology is exclusion. Exclusion of the phenomenology means that when we experience consciousness, any moment is the way it is, nothing more or nothing less. So for example, what this figure depicts is that we just can't or we don't experience the world without color, but we always experience it with color this way. And we don't experience the thing with color and all the vision plus blood pressure. This is supposed to be the blood vessel. Something that we cannot experience is always outside, and something we cannot experience that compose our experience, such as black whiteness and so on, which we cannot just directly access to, is also not our experience. Both space and time and also feature and many things there is some certain boundary of experience, and that particular boundary is the one that we are experiencing from our intrinsic viewpoint. That's what it means. So after this existence, we have four characteristics that specifies and also commonly characterize any moment of conscious experience. That's the phenomenological axioms of the IIT. And then this next one is to the mechanism of consciousness part. So what IIT tries to do is after identifying these characteristic, it tries to translate these properties into mathematical formulation, so that what kind of mechanism can support support this type of the features, such as existence, composition, integration, information, and exclusion. And eventually, I'll give you this, sort of the very basic summary first. It proposes that the large quantity of the integrated information corresponds to high level of consciousness. So if we are awake and experiencing something compared to sleep and then not dreaming or anything, or under the general anesthesia, or we have a brain lesion to become complete vegetation, unlike that, our high-level conscious awareness is supported by the large quantity of the integrated information. That's first. And this largeness, or the quantity, is defined by the largest clusters of integrated information in the brain. So there is IIT proposes that there should be some locus of the consciousness, and that has a clear boundary, and that specifies this largest quantity of integrated information that corresponds to one particular level of consciousness. So up to this, it is exclusion and also information kind of idea. And then most importantly, IIT also proposes that distinct quality or qualia or patterns of the integrated information that is composed or that is specified by all the members of these largest clusters is corresponding to each type of the qualia that we are experiencing at the moment. So roughly speaking, if there is a phase percept that I have right now, then there should be something that supports this particular configuration of the system that is included in this largest cluster, and that supports this particular shape for the phase qualia. That is a sort of a upshot of this IIT theory. Okay. And then let's go from one step by step. So I'll take a couple of examples: informativeness, integration, and the exclusion one by one. So informativeness, I said that it can be considered as a one out of many possibilities. And a phenomenological observation, any of the moment that we have, be it dreaming or hallucination or thinking or feeling emotion or seeing something briefly, it is always that is extremely informative or differentiable in a sense of this informativeness. What I mean is that I'm now seeing this display and making lecture, and I'm not at the beach, and then I'm not at the lecture theater, and I'm not sleeping. All these possible experiences that I can have, I am experiencing this one. So out of many possibilities, I'm like this right now, and that is the sense of this informativeness. Okay, and then that means that any mechanism that supports conscious experience must have differentiability or a large capacity of possibilities information. So just to give you an idea, I'll give you one thought experiment. And this is a human versus photodiode introduced by Tononi in a very first paper. So single photodiode which detects the light and then becomes on state, or if it doesn't detect the light and then goes to the off state, on off two discrimination can be considered as one bit of informativeness. Okay, and then single neuron if we consider its firing spike or not as an on or off state, then it can be also considered as 1 bit or not per state. And I'm adding this question mark because a single neuron can have many more states than one on or off, but I'll just leave it for now. And then considering our own brain, as I mentioned in earlier lecture, at least within the cortex, we have 86 billion neurons, and that's roughly speaking 10 to the 11 neurons. And if each of the neuron can have on or off state, it corresponds to 10 to the 11 bits. And so in terms of the differentiability or possibility of the states that brain can take, it's much humongously different from a single photodiode, 1 bit versus 10 to the 11 bits. And that's why, one first reason to suspect that, brain can sustain informativeness, but a single photodiode cannot. Okay, so the next part. The next part is integration of experience. Sometimes it can be called as a unity of experience. So the phenomenological observation is that any moment of conscious experience is always integrated or unified and experienced as one. And this suggests that any mechanism that supports conscious experience must be integrated. And one thought experiment that points to this is comparison between human versus a digital camera. A digital camera has, currently the high-end digital camera seems to have 10 to 20 million pixels, and that's 10 to the 7 pixels. And in the humans, we have 10 to the 11 neurons. However, the difference between these two entities is not only the scale, but the way each of the pixels or neurons are connected. In the brain, each neuron is connected to at least 1,000 to 10,000 neurons, and it's a connectivity that makes it difficult to separate each of them. So this is one, exemplar kind of, idea. So if you have now camera, and then that sees this, sees in this means it's not really like conscious seeing, but it's capturing this scenery. And then each of the photodiode is sensing some information to the next layer of the processing. For this system, it doesn't matter if the system is cut into the piece and then separately processed, physically, and then let's say store this image in the hard disk. There is no change in because of the separation of the pixel in one area to the other or not. That's the meaning of the split in the camera case. On the other hand, in the case of the human, who sees this scenery through their brain, then it's a completely different kind of story. What it means is that if you split the brain, then as we discuss in next week, split brain patient can experience this one scene as a two separate, independent perceptions. And here, one interpretation of this split brain patient's consciousness is that the consciousness itself splits into two. It's very different from the split case of the camera. And the reason is that our conscious experience must be integrated, and the physical substrate that supports this, if it's not integrated, then consciousness itself is not going to be integrated. But in its own, each consciousness, they are supported by some kind of integrated subsystem, such as left hemisphere here and the right hemisphere here, independently. So rough idea so far is that the integrated information called the big phi, it's a capital letter of the Greek letter phi, phi, and pronounced as phi, and small phi, it's patterns of integrated information composed of a small subset of all these, entity within the boundary or sort of local minimum of the systems. And these constitute this large big phi that corresponds to the level of consciousness like awake. and then small phi patterns that constitutes sort of how exactly these, one neuron contributes to other, or two neurons specifies more than one each, or how these three contributes uniquely compared to all these possibilities of the two pairs of the neurons. Each of these specifies the information, and this high informativeness or differentiation, at the same time, a highly integrated system specifies and also supports this integrated information of this system. On the other hand, if you have a homogeneous network where each of the neuron is connected with others, with a uniform, strengths of the enhancement and inhibition and excitation, and each of them are, not unique, then each of the subset doesn't specify unique information, and that's low in terms of information. And also any subsets also are also similar to any other subsets. That's also very low in terms of uniqueness or differentiability. And these are the case where the phi value becomes small due to the low information. It's highly integrated, but there's no differentiation. And then another case is this situation. So the number of the elements are 8, and it's the same across all of these three systems. But here, each of the two neurons are connected to each other, but not across. So any kind of information that is stored or processed within here is not going to be delivered to other, and that's a case of the low integration. So either low information or low integration contributes to small phi, and then it eventually specifies very poor small phi patterns, and that corresponds to low consciousness, low level of consciousness, and no conscious perception. And then finally, exclusiveness of experience, or the border of consciousness. The phenomenological observation is that any moment of conscious experience is always experienced with a particular border and extent. So it suggests that any mechanism that supports conscious experience must have also a border or exclusive, and also a boundary. And again, rough idea on how we get to this is without mathematics, is that the locus of consciousness is the subset of a system that achieves local maximum of the integrated information, big phi. So here again, the 8 a neuron system that are connected in some kind of complex way. And then if it receives a bunch of neurons that is getting connected to this central system, then the way that IIT proposes that these kind of things that are not integrated or doesn't contribute to the specification of uniqueness is not going to count. And in fact, if you count all of these excessive units, then the phi value is going to decrease compared to isolating the phi value with just central part. And same goes for this motor outputs only kind of root or situation connections. So simply adding feed-forward connections like a sensory input, like eyes to the brain, or feedback connections, or feed-forward motor outputs, such as going from the brain to the motor output, is not going to contribute to increase of the integrated information. So the next question is, how can we test this kind of idea? So IIT explains and predicts that conscious states should be associated with a high level of integrated information, as I said. And how the next question would be, how can we estimate that the integrated information in the real brain? In the real brain, it's very difficult to compute exactly integrated information. And that's the ongoing topic of the research right now. But if we can stimulate the brain and measure the complexity of the response patterns, then we can estimate the integrated information of the real brain. That's the sort of idea. And that's the way we do it is going to be explained. I'm going to explain it in the next video. Okay, so how can we empirically test IIT-inspired measured consciousness? So as I said in the last video, our brain is too complex and gigantic to actually compute the measure of integrated information. However, with a clever thinking and also tricks, various approximations can be made for the measure of the integrated information. And the question here in this video asked is that can the measure inspired by IIT be used to distinguish the presence or absence of consciousness in the brain lesion patients, patients under general anesthesia, and people in sleep? And if that's possible, then that will lend the support for IIT indirectly. So the key idea here is to stimulate the brain using a TMS, transcranial magnetic stimulation, and then record the activation induced in as a sort of electroencephalogram, EEG, to estimate the integrated information. This is three examples of high integrated information with inhomogeneous connectivity, but still connected as a whole to make a big boundary. And another one is that highly connected and integrated, but doesn't have a much differentiation. And another one is that a disconnected system. And this phi estimate should reflect this to be the highest and this to be low and then low. That's a sort of clear prediction from IIT-inspired measure. So let's start with a situation where we stimulate this particular system, hypothetical system, with a TMS. And then if you, in this situation, the system is, doesn't have an integration, loss of integration situation. And therefore, it's expected to have a low integrated information value. And then if you stimulate this, unit number 1, because it's only connected to this, number 2, it can enhance each other or, propagate. But as the time goes from right to left, the initial activation should be, go down relatively quickly. And as a result, if you measure the EEG activity from each of these, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8 systems, then 1 or 2 can be activated initially by this TMS stimulation, but 3, 4, 5, 6, 7, 8 remain silent. That's one prediction of this TMS EEG experiment applied to the system number 1 in a disconnected system. Then now, what happens if you look at the system that is connected too much and the inhomogeneous? And here, because of the homogeneity of the system, it doesn't have a differentiation, or otherwise, it lacks information. Here, stimulation propagates everywhere, really, strongly and uniformly, and then it gets activated initially. But because of the potential, inhibition, excitation balance, and so on, it remains to it goes back to the baseline situation quickly, and then remains silent as the time goes from right to left, and that would correspond to this homogeneous activation, and then going back to the baseline quickly. And then finally, this kind of a complicated connectivity pattern, which attains a high level of integrated information. In this case, if you stimulate one part of the brain, then it can propagate to these areas and then activate this pattern, number 3 or number 5. And then each of the 3 and the 5 can activate this 5, and the 5 activates to this, and so on. And then that leads to this situation. And meanwhile, maybe 3 and the 5 can become silent without any further activation. But these two, 7 and 8, next activate 1 and also 3 and things like that, 1, 6, and then it propagates like that. So as a result, the prediction is that the activated pattern propagates across all the brains, connected brains, and then shows the complex pattern of the activity like this way. So these are the 3 predictions of a TMS-EEG experiment when applied to the human brain with loss of integration, loss of information, loss of integration, loss of information, and high integrated information. Okay. The way the experiment goes is like this way. So first, the patient or subject will sit in a chair and then equipped with the high density EEG monitoring system, and that is compatible with the TMS stimulation. Okay. And then the TMS is held by this kind of mechanical device, and then it's connected through this really thick wire to generate this massive magnetic pulse to the coil here. And then the location is controlled by some kind of system, neurobehavioral systems or something like that. And as a whole, it tries to generate an index called perturbational complexity index, PCI, as I explain next. And this is the rough schematic of the principle of the transcranial magnetic stimulation very quickly. Basically, it tries to, it generates the magnetic pulse across this, circular coil, and that induces, the electrical current is passed through this, coil, and that generates a magnetic field indicated by this, red rings, and then that further induces the electrical activity in the brain, indicated by this green arrow. So that's how the magnetic pulse can be used to activate brain. So this is the hallmark experiment along this series of experiments performed by Marcello Massimini, currently in Italy. Initial paper was published in Science. And Tononi was also who was the proposer of IIT. I was directly, the person who was behind this experiment to design this experiment. And it's worth noting that before their experiment, TMS and EEG was considered to be possible to combine, unlike relatively easy, but it's technically also difficult compared to TMS and fMRI or EEG and fMRI. And even if you can combine this technique, if you don't have a right question, then there is no reason why you want to do this, basically. And here, the idea is to bypass any kind of sensory stimulation and motor output and directly stimulate the brain and then measure the complexity of the connectivity and activation pattern through stimulation evoked EEG. So here, the A part corresponds to the location of the TMS. Here is the anterior right side of the more above the frontal areas, and that's the location of the TMS. Okay, this is sagittal and also axial and coronal slice. And then red is, so this figure in B is showing each of the electrodes EEG recording from channel 1 to channel 60 or something like that along this y direction, and each of the diffraction corresponds to the diffraction of the EEG measurement. Okay, 200 microvolts here, and the x-axis is the time that goes from here to there. And then, as you can see, TMS pulse was applied in a red, vertical line. And each of the TMS pulse is separated by roughly like 2 seconds or so. And then during the wakefulness, if you do this experiment, after stimulation, it doesn't look like nothing happens. And this is usually true for any kind of stimulation experiment which uses sub-threshold stimulation. It doesn't evoke muscle artifacts or phosphine or something like that. Usually online, you should not expect strong activation induced by TMS, except for the artifact caused by the TMS. And they remove this artifact really skillfully. So you don't see much happening in the, by the TMS in a single trial. On the other hand, non-REM sleep, where subjects are supposed to be not sleep, dreaming and in a deep sleep, the brain is actually highly active. And that's one of the things that I started off in this lecture. Activation, you know, in terms of many different kind of definition, doesn't seem to be lower in any way when you lose conscious experience in the non-REM sleep. It's highly kind of, you know, active. And then after the stimulation of TMS, you seem to see something like, you know, coherently going, you know, activated here. And then around the same time, it's also activated somewhat, you know. It's a bit difficult to see still, but something is happening around the time of this kind of, you know, going down of the response around here as well, okay? And it's very difficult to see on a single trial, so what they did is averaging across the trials. And then focusing on one particular electrode that is just under the TMS, okay? One particular electrode under the TMS stimulation. Here's the average of, smoothed average of the electrical activity that is invoked by the TMS, okay? So y-axis is the 450 trials that are transits from wakefulness to stage 1 and 1 sleep, and then this is an N2 sleep. And then up to here, you know, each of the trial is noisy, but it's averaged over the 5 or 10 trials along this vertical direction. And then you start to see some kind of, you know, evoked pattern within this, you know, wake period. And that is clearly seen by this voltage plot, not the color plot in here. So this particular electrode seems to show that after the TMS, it goes up and then down, up, down, up, down, down, and then up and down, up, and so on. And this red line corresponds to the sort of the baseline activity, and above and below means that there is something significant happen. And then during the N1, at the onset of the sleep, where you might experience some kind of dream or so, or hallucination, there is some kind of activation, but it also goes down really quickly. And then in N2, where most people do not report seeing dream, at least 50% of dream, the sleep, there they found actually the activation by the TMS is actually larger initially, as you can see in this red part. So that is reflected in this large deflection here. But it also goes down and go back to the baseline quickly compared to the wakefulness. And this is consistent with what you know, the theoretical prediction of the TMS EEG experiment was making about one particular electrode in the high integrated you know, system. High integrated system should show something like this, and then low information system, homogeneous kind of system should show like this pattern. But to get to that kind of pattern of activation, you need to see all of the electrodes at the same time. That's this next slide. So here, each of the figure component is complex, so I'll go through one by one. The first part here, the top row, is depicting the ERP average across many trials during the wakefulness. And each of the line corresponds to one particular electrode or channels. And there are 60 channels superimpose each other. And sometimes it's called the butterfly plots. So what it means is that, you know, as in a previous figure, if you look at focus on particular electrode, just beneath the, you know, TMS, it goes up, down, up, down, up, down, 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 and so on. And then, so that corresponds to something like up, down, and then going up and then down kind of electrode. And then you need to superimpose all the electrodes trajectory, and then you see some of them go up, some of them go down, and so on. And then if you plot this magnitude as an height kind of plot, then you will see the second row of the figures. And here, the red one corresponds to either higher or lower activation, and then you can see it as, you know, this density of the line corresponds to the strength of the change over the time, over the space. And then each of the figure corresponds to a snapshot of each of the particular significantly modulated spatial pattern of the responses, and so on. And as you can see, what's important here is that the propagation of the activity goes, you know, from right to the left and so on in a complex manner. And the last one is called current source density or source density estimate. Using some computational technique, they were able to estimate how the activation spread based on this algorithm. And then here, this is 10 milliseconds after the stimulation. It is first activated. The neurons or neural structure beneath the TMS is activated first, and then that propagates to the front, to the left front, and then goes back to the back of the brain, and then come to the left again to come back to the initial part of the stimulation, and so on. And then at least it goes on and on up until 300 milliseconds or so. That's the wakefulness status of the TMS evoked EEG patterns, spatial temporal patterns. And then the next one is the pattern generated by TMS during the non-REM sleep. Again, non-REM sleep with most of the time, you know, dream is not experienced. And here, initial activation is stronger than the wakefulness, as I mentioned. You know, the magnitude is much, much bigger here, and that's I'm going to ask in the quiz. And then after that, it propagates a little bit, but you know, it dies out also really quickly, and it doesn't move in terms of the spatial location. So this is corresponding to the situation of this too much integration and loss of the information or differentiation situation in the theoretical simulation I mentioned above. And this is a sort of a schematic summary of the known result when this group, you know, Massimini's group has tested many various different kind of state of consciousness. And here's a schematic result. So here first, wakefulness, you know, if you stimulate this particular area of the brain by the TMS, then it propagates to other areas and also sustains activation for a longer time. And during the non-REM sleep, sometimes you know, weaker stimulation, like 90 volts per meter, that it shows activation only one pattern and then one location, and it doesn't propagate. If it's too strong, then it goes to many areas at the same time and then propagates, but it dies out as well quickly. Okay, so then what happens when they did the experiment when people are dreaming in a REM sleep state? So it's almost like in a wakefulness situation. A little bit of the stimulation in one area propagated in many other areas, and then it doesn't come back to the baseline for a longer time. And under the anesthesia, where researchers know that people lose consciousness, then it's similar to the situation of the non-REM sleep. Stimulation by 120 volts per meter, doesn't propagate much and then dies out quickly. And then, most critically for the clinical purpose, vegetative state or unresponsible wakefulness states, these are the people who do not seem to have consciousness in many criterion. They have similar type of local disconnected type TMS response, like anesthesia or non-REM sleep in this situation. And the minimally conscious and the locked in state patients, they show much more reliable signals of consciousness. And the lock-in syndrome is the one that I showed the video in the earlier videos, and they are fully conscious, but just cannot move. And then they are almost like wakeful subjects. Minimally conscious patients who fluctuates in conscious experience or conscious states, but when they are tested with the conscious state, they show similarly complex pattern of the TMS evoked EEG patterns. So as an interim summary, TMS evoked EEG patterns were expected to differ depending on the brain states. High integrated information system should generate more complex TMS EEG pattern, and the low integrated information system should generate less complex TMS EEG, either activated all the time or activated only parts of it. And then both of them were confirmed across different types of loss of consciousness. And then the next question would be, can we construct a consciousness meter based on this idea? And that's what I'm going to talk in next video. Okay, now how can we construct a consciousness meter or any kind of clinically possibly applicable measure of consciousness out of this TMS EEG paradigm? So what the group has proposed is an index called a perturbational complexity index, PCI for short. And how it does compute this is the following. It's a bit complex, and I'm not going to ask about this in the exam, but let me explain the following. So first, we get this TMS evoked EEG from each channel as this butterfly plots, and then that is projected onto the surface like this way, as you saw before. And then they do this source localization or source estimate of the statistical significance. And then they binarize the significance threshold to be either significantly activated or not in the end. And then that is now converted into time versus significance kind of a map of the two dimension. And then use this zip algorithm, sometimes called a Lempel-Zip complexity or complex zip algorithm, to compress this resulting statistical significant image, and then quantify the pattern of the activation as a complexity. And then they use this normalization protocol to eventually come to this number, a PCI number of 0.55 in this case of this result. Okay. So what can we get out of this? So first of all, when this Casari and colleague have applied this to the wakefulness situation in one particular subject, then each of the electrode has a significant, departure or source level, signal. Have a significant time points of the activation, like here and here and here, and then maybe closer to the TMS activated area, there will be a longer and more complex level of the activation pattern. And this time point that exceeded some statistical threshold will be depicted as a black point in here. Okay, that corresponds to these significantly activated source patterns, as you can see here. And this is now compressed by the zip algorithm, and then this pattern visually looks complex, and it's not possible to compress, or but by compression, it means that when there is lots of redundancy in the patterns over the time or space, it will be compressed, and they're replaced by the copy is replaced by the original kind of idea. And here, because each of the pattern of the activation is unique, more or less, it gives rise to relatively high level of this PCI value of 0.51. On the other hand, when they get the same results from the non-REM sleep with the same level of activation or stronger activation pattern, then here's what we find. So if it's very small, like the same level as wakefulness 90 volts per meter, then only small amount of the electrode gets activated. Remember, it's similar to the situation of the disintegration. And then that will result in this small amount of the electrodes and the source to be activated briefly, and then it dies out also quickly. And then this resulting pattern is much simpler compared to this more complex threshold pattern. This is simple. And if you convert this into another, another file using a zip algorithm, because there is a lot of white space here, it can be easily compressed, and that result in the smaller number of the PCI 0.23. And then another situation where they stimulated the brain with a stronger amplitude, 160 volts per meter. Then it invokes a strong activity across all the areas, but it also dies down uniformly. So this is a situation of too strong integration and the loss of information differentiation. Okay, and then in this case, the pattern of the result looks much more darker compared to the wake state here, but because most of the patterns are really similar from line to the other, it turns out that it's also easy to compress by the zip algorithm. And that easy compression results in the smaller value of the PCI, 0.21. Okay, so the pattern of the complexity of the activation was now quantified by single number PCI. And that is an estimate of big phi, the amount of the integrated information that is likely to be correlated with the consciousness level. But this is not the same as the pattern of the integrated information, as I explained next week. Okay, so this is a gigantic experiment performed by and also accumulated over the many years of this TMS-EEG experiment by Marcel Masmini's and the group collaborating with across doctors and so on. And the Casarotto has tabulated all this experiment effort in one paper. So here, the first starting point of this paper was behaviorally confirm the case of the responsive or conscious state versus non-conscious states. And the behavior confirmed the responsive states, of course, it contains a wakefulness situation. And then each of the column corresponds to each subject, healthy subject here. And then as you notice that each of the subjects were tested multiple times. And then each of the subjects has participated proposally like 4 times, I think. And you can see, for example, here or something like that. And then they took the maximum level of the PCI as PCI value for that particular subject. And this is because that maybe this PCI didn't work in one session due to the noise in the equipment or non-optimum angle of the stimulation or many kind of different artifacts. So they argue that maximum across 4 repetition is more reliable way to define this perturbational complexity index for that particular subject per state. Okay, so this red value is the maximum among several iterations of this TMS-EEG experiment and computation of the PCA value. And in a wakefulness situation, it's always bigger than this threshold line, this dotted line. Maximum is larger, but sometimes there are some cases of lower than this threshold situation. Okay, and then on the other hand, behaviorally confirmed unresponsiveness is represented in this non-REM sleep. So here, subjects later on, I'm not so sure exactly whether they confirmed verbally or recollection upon spontaneous awakening, but when they repeated 4 times of the measurement, in some cases, sometimes only measured once, it seems. But the maximum value of the PCI is below this dotted line here. And then another types of the reported, unresponsiveness or non-conscious state is 3 kinds of the general anesthesia: midazolam and xenon and propofol. these are tested for different, separate papers, and then each of the result is explained in more detail in each paper. But here, again, the PCI value seems to be lower than this dotted line. And the propofol case, they measure the PCI at least multiple times for some of the subjects here. And it's always maximum of the measurement is below this dotted line. And then next is this delayed report. So here they use both sleep, REM sleep situation, or ketamine. This is another general anesthesia drugs. And each of these cases, these experimenter can confirm later on the presence or absence of the consciousness from the subject. And in the case of the REM sleep, roughly more than 90% of the situation of the REM sleep is associated with dream reports. So we can safely consider that they are conscious states. And then there, if you do the TMS-EEG experiment during the REM sleep, then the maximum value of the PCI seems to be above this dotted line. And in the case of the ketamine, ketamine is a drug or anesthetic drugs that with a low dose of the ketamine, it induces hallucination or dreamlike experience. And then there we can also assume, or we can confirm from subjects that they had an experience. And some the paper also described this nature of the ketamine-induced hallucination. And then again, PCI value is above this dotted line. Okay. And then another bulk of the situation is this confirmed case of the patients. Okay. I'll clean up first. So here, locked-in syndrome, as depicted in the movie, they are all conscious, and then they are repeatedly tested with this PCI, and the maximum PCI is above, this threshold value, PCI star. And then subcortical stroke. So when the stroke happens in some of the subcortical areas that does not impair consciousness, then they also can serve as a control subjects. And EEG or TMS is difficult to interpret for these patients who have an injury in some part of the brain, but this TMS EEG methodology, as well as a PCI computation, can be applied to the patient who has the brain damage. And from them, again, the PCI measure is above threshold line when they take the maximum value. And then cortical stroke, here, in some cases, brain lesions are very close to the surface. So it can be difficult to measure the EEG, but still, in terms of the complexity and stimulation of the location, as long as you avoid stimulating the locus where there's no brain matters due to the stroke, then you can measure the PCI value in a reasonable way. And then there, they also found that most of the cases, actually all of the cases above PCI star when they take the maximum value. And then this EMCS is an emergence from minimally conscious states. So these are the people who recovered from the massive lesion, brain lesions, and under the minimally conscious state. And then they became more stably conscious. And again, these conscious people can show this, PCI value above this threshold value. So this first subset of the experiment, or measure of the PCI across normal people in sleep and anesthesia, where we can find we can make sure that they are non-conscious, or sleep and anesthesia plus wakefulness as well as the brain lesion, where we can confirm presence of consciousness. So in the case of this situation, the reliable threshold turned out to be, according to this paper, is 0.31 PCI star. And below that, the confirmed cases of the non-conscious result in this, below 0.31 PCI, and the reliable confirmation of this maximum PCI is above 0.31 for the awake situation. And then Now that they have established this threshold for confirmed case of the non-conscious and conscious, they now apply to these unclear cases of the clinical border of the conscious and non-conscious states. So this is the result. Here, first, they review the PCI value in a histogram. So these are the confirmed case of the non-conscious through general anesthesia and also sleep. And here is the delayed or immediate report of consciousness in the wakefulness, a lesion, or REM sleep, or ketamine. And then these, the left, each of the line again is each subject patient number, and then all of them are receiving lots of brain lesions, and very difficult to determine their conscious experience. And the minimally conscious state plus and minimally conscious state minus are those people who are considered to be in a conscious state through highly intense clinical measurement on the repeated measurement or assessment of the consciousness. And these are established through this coma responsiveness scale revisited, CRSR. And that value is going from 18 to 7. That's a sort of the classic categorization of conscious patients among this coma like states. Okay, and then up until here, according to this this CRSR and also multiple criteria, they are considered as a minimally conscious state plus. And then from here, this patient up to here is at 7 to 14 in terms of CRSR, but classified as a minimally conscious state minus. And then, as you can see, for each patient, they did the multiple measurement of the PCI, and it's more or less it's above 0.31 PCI star, which was established from different patients, different subjects in conscious, non-conscious states. But two of the MCS minus patient here and here was below the level of PCI star. And then the behavior unresponsiveness situation, where those people who have scored CRSR below or equal to 7 or something like that, and they are classified as vegetative states or unresponsive full wakefulness. And most of these patients are below 0.31 in terms of multiple levels of the PCI measurement. And notably, some of them have maximum value of PCI of 0. Okay, this black thing are the patient whose brain, upon multiple examination of this TMS EEG, it just doesn't show much response. So it's relatively easy to consider as a sort of non-conscious brain. But some of them have above 0 PCI, but it's very brief and small, and it's similar to the level of the general anesthesia or non-REM sleep, even multiple times of the examination. But some of the vegetative state patient, like these and these and these, do show above threshold, PCI star, PCI value. And some of them are, in the end, actually recovered from the vegetative state into the minimally conscious states. So it's plausible that the PCI may be used in the future as a sort of the way to infer or predict, use as a prognosis of the patient's, recovery from non-conscious state in a vegetative state into the minimally conscious states. And this level of the specificity and the selectivity of the detection from minimally conscious from vegetative states is, much better compared to any other method that has been proposed so far in the field. So this is like currently most reliable way to measure the consciousness in patients who just cannot communicate as reliably. So in summary, in the last part of the video, I showed that the PCI values were lower than PCI star threshold in the known states of loss of consciousness, including brain injury, such as vegetative states, or general anesthesia, midazolam, or xenon, or Prop 4, as well as sleep in the non-REM period. On the other hand, PCIs were also higher than PCI star in the known states of consciousness: wakefulness, brain injury, minimally conscious states plus and minus, and locked-in syndrome, and so on, as well as the ketamine anesthesia and the REM sleep. And the way they derived this PCI star first was coming from the case where they can establish this gold standard through the reports, and then apply that the threshold to this patients who cannot report directly. And this TMS-EEG based paradigm is currently most reliable in discriminating loss of consciousness. And the reason why they can do this or achieve this is for several reasons. One is simple, that is that skipping the sensory or motor areas. Compared to the clinical way of clinical currently used bedside assessment of consciousness, TMS-EEG stimulate the brain directly and then measure the brain response directly with the EEG. And this does not rely on the communication with the patient. So if you imagine the detection of consciousness in the clinical setting in most of the situation where they ask patient, are you conscious, or can you move your eyes, or can you move your hand or shake the hand, or whatever. This relies on the communication, right? So you can imagine that patient, like locked-in syndrome patients, who just doesn't have a proper auditory sensory cortex, wouldn't be able to react to such an instruction. And also people who lost motor command to the hand or eyes or something like that, they also have no way to communicate with the clinicians to for their understanding and also consciousness to express their conscious experience. Therefore, some of the it's kind of scary thought, but if you go into the let's say if you are having a traffic accident in the future, and then if your sensory or motor areas are critically damaged but remain conscious perfectly, then unless you do this kind of probing, stimulating, and also recording from the brain directly and determine conscious experience from that, you may not be able to be treated as a conscious entity. And that's something that I showed in earlier part of the video on the patient's report, right? And some of the existing technique in the neurology is still using this type of the sensory or motor command, not only verbal communication, but like auditory evoked sound, sound revoked response, or motor activation is taken as a presence of consciousness. And remember that I talked about the visual imagery experiment in the week 1, where they asked presumable vegetative patients to imagine playing tennis or imagine walking around, and then they could activate brain areas through the fMRI. But that also strongly depends on the part of the sensory areas to understand the instruction, first of all. And another one is to depend on the premotor areas that are critical for imagining this movement. So if either of them are damaged or not really sufficiently recovered, then that fMRI-based imagery experiment or method cannot be used as a measurement of the sensitive measurement of the consciousness. And also another possibility, which relates to next week's idea of consciousness as a possible repertoire than the actual activity pattern, is that this TMS-EEG paradigm is also unique in the sense that it is based on the evoked activity rather than spontaneously observed activity. You can imagine a situation where brain activity gets into trapped into some situation, and then they just remain silent or remain oscillatory for a long time, and then that leads to loss of consciousness. But TMS perturb and activate the areas of the brain so that it tries to see how much brain can do possibly. And maybe that's the reason why we can quantify this conscious level much more reliably than the other types of the measurement. That's another issues, but that's with a question mark. And then also, most important or most interesting possibility is that the TMS-EEG is in fact reflecting the integrated information, even though we cannot compute exact integrated information of the brain. This is a really good method to estimate overall integrated information. And if the integrated information is really a good, explanation of the consciousness, then it makes sense that the TMS-EEG does reflect the consciousness. So the remaining questions for the next week is that what about the IIT's predictions on the boundary and the contents of consciousness? I started this lecture with promise of the IIT's prediction about what part of the brain is responsible for consciousness. And in fact, in the earlier part of the lecture, I talked about the patients who lost a prefrontal cortex, or patients who were born without cerebellum, but both of them didn't have any problem in consciousness. So that kind of clinical observation and how IIT explains where the consciousness should be located, the boundary of consciousness issue, how much is it consistent with our actual observation. That's one question. And the contents of consciousness, as I repeatedly emphasized throughout the lecture, why face perceive gets generated from the FFA, or color from B4, B8, and then motion from MT. How can IIT predict or explain this kind of the difference? That's another question. And so that's this part. How can IIT, in principle, explain why different areas of the brain differentially contributes to different aspects of consciousness or qualia? And then, if you find this direction of the research interesting, then you may also want to investigate this empirically. And if you go into the empirical direction, then the next question is, how can we measure integrated information in the first place? And then how can we test the entire theory of IIT? Is it actually reasonable theory of consciousness or not? That's the question that we are going to touch upon. We can't really address all of them in the next video. Until then, see you.